have some velocity, and of course that point has some acceleration. So in our last class we talked about the relative velocity method, and we solved two problems, I hope, that and how to explain and how to solve these two problems, and we emphasized on the semi-analytical method because we saw that that particular method will try to give us the result in a quicker manner. So today we will continue with that thing. In fact, we will be talking about today the what is called the relative acceleration. Now, if we come to this case, I told that I actually, the PDF that I sent to you, in fact, that has the had that acceleration equation. I hope I told you that you please go through it. Just have a cursory look because I will be explaining today this thing. Although the basic equation has already been explained in connection with our discussion with system of mass particles, particularly when we talked about at the end, when we talked about the rigid unit, two particles connected by a light rigid rod, some kind of thing like that. Now here, this is today we will see that this is the acceleration analysis, and certain things we need to just recap. That we said that the relative velocity of any point B with respect to another point in a rigid body will have this equation with respect to a translating reference frame. We'll have this equation. Why this equation is coming? It is because of the fact that the point A and B, the distance between these 2 points belonging to any rigid body, is basically constant. So it means that with respect to some point, let's see that with respect to suppose the point A, the point B belonging to the rigid body, suppose if we have here a point A and then here we have a point B, so if this is A and this is B, then the distance between these 2 points A and B, this is always going to be constant. And since it is always going to be constant, the motion of B as seen from the point A will be a sort of circular motion like this. So as a result, we see that the magnitude of this vector, so the magnitude of this vector is not going to change. Only thing what is going to change is thing that is going to change its direction as the point B changes its location. Say it comes to B prime. So obviously you see the vector comes here. The magnitude of this vector and magnitude of this vector will be same because both of them will represent the distance between the 2 points. And since from the rigidity definition this is going to be constant. However, since there is no change in magnitude, but we do have the change in direction. So it means that this is the change in direction. So this change in direction vector is actually being given by this particular equation, which will be due to the circular velocity of this point. So the circular velocity, you see here, the tangential velocity, so to say, will give you the change in direction between these 2 position vectors, and the rate of this will be given by this particular equation. So this is the equation that we need to remember. And the second equation we do have is the relative velocity equation between the 2 points A and B with respect to the reference frame, which is of course translating one. So under such circumstances, we note that this is our equation. Now if we differentiate this equation with respect to time, obviously what we get, differentiating the velocity of point B with respect to the time t, you see, will give you the acceleration. So we have A bar B, and that will be equal to, obviously if you differentiate now the velocity of A with respect to time, it will be giving you the acceleration of A. And then we have that the first 2 terms are easily understood. Now you need to differentiate this term, and we will be doing it by U and V method. So the first differentiation is of course the differentiation of angular velocity with respect to time. That will give you this omega bar dot cross, this one will be unchanged, and then we will be going to differentiate omega bar cross rho bar b relative to a dot. Now omega bar dot, the other day I was telling, since we are dealing with a plane motion, omega bar dot is actually the angular acceleration of the body. So this is the angular acceleration, and how the angular acceleration will be found. Now since your body is actually executing plane motion, it means the direction of angular velocity always remains the same. Only thing that changes is its scalar magnitude. So as a result, the scalar magnitude of angular acceleration is equal to the time derivative of the scalar magnitude of angular velocity. And we can see that, but I told that the other day I was telling you, when you discuss, you will be discussing or studying the three-dimensional motion in your next semester of the rigid bodies. There you will find that the angular acceleration term is not so easy. It will be having the direction change component also, because in three-dimensional motion the angular velocity continuously changes its direction. So as a result, you have other components to this angular acceleration expression. However, for us it is simple. For us it is simple to note that angular acceleration is simply given by this. So this is basically, so I can say from here that alpha bar, that will be equal to, you know, omega bar dot. And in plane motion, if we suppose our motion to be as xy plane, plane of motion has to be the xy plane, then the angular velocity or the angular acceleration will be either along positive k cap direction or it will be along the negative k cap direction. All these things we have already told in our previous class. So you see, now going back to the second line, if you find that these terms are all retained like this, now it is the thing that we know that rho bar b relative to a dot. Since this is being given by this expression, we can bring this expression here and pre-multiply this expression by omega bar. So pre-multiplying this equation will have therefore, you know, the three-term acceleration. So I will be having a bar b, that is equal to a bar a plus omega bar dot cross rho bar b relative to a plus omega bar cross b bar a, you know, this vector. Now we can see, of course, you know, this particular thing, to it I have to add here, to it I have to add acceleration of a. So it means that, sorry, acceleration of a. So these two terms taken together, that means if I see, if I say like this, if I take these two terms this way, so if I take these two terms here, and you know, these terms can be written in this manner. The first term is written as a bar t. This is called the tangential acceleration, and this one we'll call it as to be the normal component of acceleration. To it I have to add acceleration of point A. The point A is not visible here, so I like to write it properly for you. This is acceleration of point A. So as far as the plane motion is concerned, the next simplification, I mean to say, from this equation to this equation is, of course, it is valid only for plane motion. This is not going to be valid for the three-dimensional motion. So you have to be very careful that this simplification is for only plane motion. So that is why we have written it here. This is for plane motion only. For plane motion only, we must say. This is for plane motion only. So we see from here that we note that the terms can be written as, especially the last term, that means omega bar cross b bar rho bar B relative to A, this term can be simplified, particularly if someone follows the vector triple product. He or she can be able to simplify this equation to this format. So I say this is called the tangential component of the acceleration, and the last term is called the normal component, and you see this negative sign. So the negative sign indicates that the normal component of acceleration will be directed towards the point A. So this is actually the direction of rho bar B relative to A. This is rho bar B relative to A, this vector. So A bar B relative to A, I mean to say this one, the normal component of acceleration. The normal component of acceleration, since it is having this negative sign, the normal component of the relative acceleration will be always directed towards the point A because of this negative sign that is there. So this is termed as the centripetal acceleration. It's center seeking, and this is called the tangential component of acceleration for us. So that's why we write it as the tangential component plus the normal component plus the acceleration of point A. So if you say,
বলছি স্যার এই ভেক্টর ট্রিপল যেটাতে করলাম ওখানে আরেকটা টার্ম থাকবে, ওটা স্যার কোথায় জিরো কেন হয়ে গেল? মানে ওমেগা ডট রো বি বি বাই এ আর ডট
বি বাই এ না, বি রিলেটিভ টু এ,
বি রিলেটিভ টু এ ওমেগা, স্যার ওই টার্মটা জিরো কেন হয়ে গেল? হ্যাঁ,
কারণ হচ্ছে তোমাকে আগেও বলেছি, সিন্স ইট ইজ এ প্লেন মোশন, প্লেন মোশন মানে কি, আর ওমেগা বারটা কি, ওই যে বললাম যে ওমেগা বার ইজ অলওয়েজ পারপেন্ডিকুলার টু দি প্লেন মোশন, কারেক্ট?
আচ্ছা আচ্ছা, হ্যাঁ স্যার, হ্যাঁ।
যেহেতু ওমেগা বার ভেক্টরটা is always perpendicular to all vectors,
so তাই জন্য ডট প্রোডাক্টটা জিরো হলো,
ডট প্রোডাক্টটা জিরো হয়ে গেছে।
কিন্তু
আবার বলছি, it's a very interesting question that you have asked, but this is not going to be true for space motion. সুতরাং স্পেস মোশনের জন্য এই থার্ড লাইনটা মানে লাস্ট লাইনটা কিন্তু we cannot write, right?
Okay sir.
So you must not overlook this scenario. This is a common mistake people often make when they try to solve the three-dimensional problem. But in case of 3D motion, that perpendicularity relationship between the angular velocity and the position vector is not going to be valid, and that's why the other term will be there. বুঝতে পেরেছো? সুতরাং the other term will not become zero. Yes. So that's why the other term becomes zero and we have this negative sign. So I think you have understood.
Yes sir.
Okay, thank you. So now if you look at this acceleration equation, what you will find is that on the right hand side you have three vectors, and on the left hand side you have another vector. So the sum of the three vectors will be equal to the left hand side vector. So it means if we try to actually solve this equation by semi-graphical method or semi-analytical method, I have to draw acceleration polygon. So instead of acceleration triangle, now it will be acceleration polygon. So we have to draw basically an acceleration polygon to solve our problem, and we will be doing it in this way. So first I think I will be solving one problem analytically, and then the other one I do not know whether I have done the analytical solution at all for the acceleration. Anyway, let's see whether I have done it or not. Otherwise actually
no sir. হয়নি, ওটা হয়নি,
না সেটা হয়নি, সেটা আমি জানি, কিন্তু অ্যাকচুয়ালি আমি সলভ করেছি কিনা এখানে সেটাও দেখতে হবে, বিকজ অ্যানালিটিক্যাল সলিউশন ফর অ্যাক্সিলারেশন ইজ এ ভেরি বিগ জব। অনেকখানি লম্বা একটা অ্যালজেব্রা। ইউ মে সি এক্সাম্পল ফ্রম মিডিয়াম এন্ড ক্রেট, দেখবে এক্সাম্পলে করে দেওয়া আছে একটা দুটো অঙ্ক মিডিয়ামে, দেখবে ইটস এ ভেরি লং প্রসিডিউর। সো ইয়েস, দ্যাটস দ্য ডিফিকাল্টি অফ দ্যাট মেথড. So I stick to the semi-analytical approach. In this case, say for example, let us take this problem from the book of Medium. It's again a four-bar linkage problem. The last class I have introduced what is called four-bar linkage. So this is again a four-bar linkage problem. So in this case, this is a driving crank. That means motion is given to this crank, to this shaft, by means of some electric motor or something like that. This actually, these are all building blocks of robots. So all the robotics that you people do normally nowadays, there is a tendency, a trend. Young people are very much interested in doing some robotics or robo hackathon, something like that. So you see, all the building blocks to that particular kind of things are this what is called this forward linkages mechanisms. So by some the external source, through the electric motor, I am giving the input motion to this crank, and I am trying to get the output motion here. So this is what is called the driving crank. This is called the driven crank, and this one is now termed as the connecting rod. So connecting rod is connecting the driving crank and the driven crank. You need to remember all these terminologies because these are important when you will be going to study mechanisms and machines. There you will need to understand all of these things, as well as when you will be studying dynamics of machines in third year. There also you have to come across all these concepts. So here it is mentioned as link OA, but I like to say that it is a crank. This is a crank, and this is what is called as the connecting rod. So link OA, this is the link OA, has a constant counterclockwise angular velocity omega that is being given here. For the position shown, find the angular acceleration of the link AB and link BC. Achha, before going into this thing, I must mention to this equation, which I have forgotten to mention, that this equation or this equation, whatever you look at, all these equations for plane motion will be having only two scalar components. So again, acceleration analysis here, the maximum number of unknowns that I can solve is limited to 2. So that is why, if we have more than 2 unknowns, then that equation cannot be solved. So you see here, the unknowns are here mentioned as determine the angular accelerations of the link AB, that means this connecting rod, and the link BC, that means this driven crank. We have to find out the angular acceleration of both these two links. Now, the thing is this, another important issue for acceleration analysis is that acceleration analysis cannot be done without performing the velocity analysis previously. So even if the question is asking for you from you the angular accelerations of these two links, actually before that you need to solve the velocity. Otherwise you will not be able to getting the acceleration equation. So first we will need to draw the velocity analysis. So here we need to solve the velocity triangle. First we take the link OA, correct, link OA we will first consider and write the equation here, because in the examination also you need to write all these things considering link OA, then write the equation. Here I have not written it, so if I am a student I will be not getting full marks with this answer whatever I have written it here. So you need to consider first the link OA and then take these 2 points and write the relative velocity equation between these two. So you can say that it can be written like this. It will be omega bar OA cross the position vector of A relative to O. Now here, since the velocity, this is fixed, so you can see that this is going to be null. So ultimately we get that it is omega bar OA cross rho bar O relative to A relative to O. So it means it is a simple circular motion. So naturally the velocity of point A is going to be perpendicular to this link, correct? So to draw the velocity triangle, we first take a pole. Let us assume that we take the pole as point A, or separately you can draw this triangle here. I have taken the point A as my pole, and remember all absolute velocities should pass through the pole. So first we draw this line which is going to be perpendicular to this horizontal line. Again, this is an instantaneous configuration like this. After time delta t, this instantaneous configuration will get changed. So whatever you are doing it for this instant only. That always you need to keep in mind. So here, therefore, the velocity of this point A will be going to be perpendicular to this link, and it should be, the sense should be consistent with the sense of angular velocity. So naturally, the arrow will be upward here. So this line is plotted. Now you consider the link AB. Now for the link AB, if you now write the equation, so it will be VB equals VA plus it will be omega bar AB cross the position vector of B relative to A. Correct? This is going to be my equation. Now of this, you know, this particular term omega bar AB cross rho bar B relative to A is going to be perpendicular to this link AB, to this link AB. So it's going to be perpendicular. So it means that this relative velocity will be parallel to this horizontal line. So what I do therefore, through the tip of the vector AA, I draw a parallel line. Okay, I do not know which way this velocity of point B will be acting. So it is therefore a prudent idea that you extend this line in both the directions. Now come to the link BC. So you see, for the link BC, since this point is fixed, so again you see that V bar B will be going to be equal to omega bar BC cross the position vector of B relative to C. So therefore, this velocity of point B is going to be perpendicular to this line. So you see this is going to be perpendicular and therefore it will be parallel to this line. And since this is an absolute velocity, so I will pass that line, I mean to say this line, I will draw a line which is parallel to this blue line or this red line through the point A, because I am looking for the absolute velocity. So therefore, through point A, I draw a line parallel to this blue line or perpendicular to this line BC, and allow, this is the black vector, that line I have drawn, and allow that line to previously drawn blue line then to intersect at point small b. So my velocity triangle is complete, for which you see this angle is going to be 90 degree. Correct? So it is therefore our triangle is a right angled triangle. Now since from the geometry I note that this angle is 45 degree, from the geometry it is seen. So therefore obviously this black vector is going to be 45 degrees. So it means that this is an isosceles triangle. So from here what I will be getting from this triangle, I say that AB will be equal to AA. And I get that AB means what? This is the relative velocity. I mean to say this velocity. Now this relative velocity equation magnitude is definitely equal to the length of this member AB, which is happen to be equal to R, multiplied by the omega AB. So this must be equal to omega into R. So definitely it gives me omega AB is equal to omega. So I find that if this is omega, then the connecting rod is also having the same angular velocity, that is omega. Okay, Achha. That is one thing. Second thing, what I want to do is I must find out the velocity of point B also. So the velocity of point B is this root 2 times the either of these two velocities. So it is equal to that. And this point velocity must be equal to omega of this length of this member into the length of this member. Now the length of this member is root 2r, so it is root 2r multiplied by omega bc, so that must be equal to your AB. So you see from here you get omega bc is also equal to omega. So that's nice. So you see what will be their directions, I mean to say their sense. see here, omega AB is equal to omega. Now you see, this is the relative velocity expression, correct? So what you do, you mentally place this vector here. So just mentally, mentally place this vector here. This, suppose it represents your r times omega AB. This is r into omega AB. Okay, this is mentally I place this vector. Now you assume, yes, now you assume that if this point is kept fixed, so how this tangential velocity will be realized? It can be realized only when your this link's angular velocity is in this direction. So therefore I find that the angular velocity of the link AB has the clockwise, this is having the clockwise sense. That means it must be, the arrow must be in this direction. Okay. Now secondly comes this link. You see this BC link. Now here you see this is the absolute velocity of point B. Now mentally if you keep this absolute velocity here, say mentally if you place this absolute velocity here, I mean to say this is BB, then obviously this velocity can only be realized if this link is also rotating in this direction. So as a result, I find that this link BC is also having, the clockwise angular velocity. So you just see the driven crank is rotating in the counterclockwise direction, but at this instant the connecting rod is rotating in the clockwise sense, as also the driven crank is rotating in the clockwise sense. Okay. So up till this part, the entire velocity analysis is done. Now we will proceed to find out. Somo Himram, he is very late today. So you see here that that if I try to enter now it is our right time to come to the acceleration analysis. So what we will do now, I will come the acceleration equation. Please remember our acceleration equation, the three-term acceleration equation that we have studied here. That acceleration of any point B on any rigid body is equal to acceleration of the reference point plus this will be the two relative components of accelerations with respect to that reference point, correct? So now you see, first we like to draw the acceleration for, let us first take this link OA. Now here O is my reference point, A is the point for which I am trying to get the acceleration. Now since it is rotating with a constant angular velocity, it is being mentioned already that it is rotating with a constant angular velocity. So it means that it does not have any angular acceleration. The link OA is not having any angular acceleration. So the only acceleration that the point A is having is the centripetal acceleration. That means its acceleration will be always directed towards the point O. So what I do therefore, let's say the point A, let's just take this as our pole. Pole means from where I am actually starting the diagram. So that is the call as the pole. So I take this pole first and calculate how much will be the angular, how much will be this normal component of acceleration of A relative to O. It will be omega square, omega OA square actually. Omega OA is actually equal to omega square multiplied by R. So it is omega square R. So we draw first this red line. So this is the red line first we need to draw. Now after drawing you need to think what are the other acceleration things you know. If you come to this acceleration equation, if you see, say for any point, now I will be applying this equation between the points A and B in the connecting rod. So if you look at this equation, you know the acceleration of point A because we just now calculated it. You do not know this part. Why? Because you do not know what is the angular acceleration of the connecting rod. So this omega bar dot is not known to me. So this is an unknown thing. However, I know this thing. So what I do, I first draw the known vector for me. So what I do, therefore, I take this blue line here, and you see the normal component of acceleration of B relative to A will be what? It will be directed towards this direction. It will be directed towards the point A, correct? So therefore, what I do, I draw this vertical up line, right? And I call it acceleration of B relative to A normal. And I know its magnitude, correct? I know its magnitude. What should be its magnitude? Now its magnitude should be equal to, it will be omega AB square, it will be omega AB square into AB. So which tantamounts to saying that it is equal to R omega square, because AB is R, omega AB is omega, we have just now found here. So it is omega square R. So this omega square R, so this is basically equal to omega square R. So that omega square, so I erase these two things and simply write it to be equal to omega square R. Why it is so? I think you have understood. So this is equal to omega square multiplied by R. Now once this is done, now you see that your tangential component of acceleration, that means this component, this component is going to be perpendicular to this component, because tangential component of acceleration is always going to be perpendicular to normal component. So therefore, because this vector is known, this vector is known, this vector is known, I get this point here, B dash suppose. Now what I do, I draw a black line which is perpendicular to it. That means this line is perpendicular and extend it both ways, this direction. Okay, but I do not know where it goes and hits. So you see, this is unknown. This represents my vector tangential component, but which way, first of all, I do not know. Secondly, I do not know its magnitude. So this is an unknown quantity. So this black line is an unknown thing. So I therefore have decided to extend it both ways. Either your diagram will be on the right hand side with respect to B dash, or it will be on the left hand side with respect to B dash. I do not know. So that's why I extend it in both directions. Now, we cannot extract any information beyond this any further here. So we stop. Now I relocate my focus to this link BC, because this is an incomplete attempt to find out acceleration of point B. I could not finish my job. Now I have to come and look that this point is also belonging to this link. Okay, so this link might be having a tangential acceleration, because here it was given to be constant, but it does not mean that this and this will have constant angular velocity. Though their magnitudes are all equal, but it does not mean that since omega is constant, these were also going to be constant. It does not necessarily mean that. So you have to be very alert, because people often make mistake that they say from here, since omega is constant, alpha AB is also 0 or alpha BC is 0. It is absolutely not, because these are instantaneous values, and the instantaneous values are always will be constants. So therefore, this will give you a false impression that your angular acceleration of these two links will be 0. So, you know, if it is an objective or multiple choice type question, definitely, you know, one option will be given to be 0 for both of them, because many people will strike that, because, you know, they have been told that your omega is constant. So from that, you know, this is a common philosophy I am explaining. Normally, these are the common mistakes that students quite often commit. So you have to understand the physics. I'm again telling you, it's very, very important, because without simply by merely going through the equation will not give you the understanding. So now you come to the point B, and now going to write the equation between these 2 points, the relative acceleration equation. At least we are saved here because the C point does not have any acceleration. So what will be therefore on this link BC, what will be therefore components of acceleration of point B? One is definitely is this component. This is definitely known to us. This is the normal component of acceleration towards point C, and I know this magnitude. I know its magnitude also. Correct? So this is of course known to me. Since this is known to me, what I do, through the pole I draw a line parallel to this. You see, I draw this line AC parallel to the link BC, because I know this magnitude, right? And this is ABN. How much is this known to us? You see, this is root 2r. So we can write this is root 2r multiplied by this link's angular velocity square of the angular velocity of this link. Now omega BC has been equal to omega, so it is therefore omega square multiplied by this quantity. So you see, this will be the normal component of acceleration of point B when it is on BC. What will be the other component of acceleration? That is going to be perpendicular, and I means or this line is going to be my direction for tangential acceleration, but the sense I do not know. So what I do, since this is completely known to me, I come to its tip, and through the tip, you remember you have come to earlier and you had drawn one black line of B relative to A. So now through this point, because I know this vector, I come to this point, and through this point I draw a line which will be parallel to this line. So through this point, what I do, I draw a line parallel to this. So this line is drawn. So this is another unknown, and allow these two unknowns to come and intersect at point B. So this is the point, and now you join all the tips. Now it is clearly known, because you know acceleration of B is equal to the sum of all. So what is acceleration of B? This is one component, this is one component. So this arrow plus this arrow must be equal to this arrow plus this arrow plus this arrow. So it means therefore that the arrows or the senses of the angular accelerations are all shown like that. Now I can decide their sense. See the first one, acceleration of B relative to A tangential is having an arrow in this direction. So clearly the angular acceleration of this link is going to be in this direction. So it will be going to be alpha AB. Now see, the tangential acceleration of point B is having the arrow in this direction, because we have already decided the sense, correct? So you see, therefore this arrow is in this direction, so this arrow is going to be in this direction. So it is only possible when you see your angular acceleration is this way. So it is going to be your alpha BC. So it is therefore obvious that alpha AB will be counterclockwise and alpha BC will be clockwise. So I have to report these two senses at the end to the answer. Now I have to find out their magnitudes. That means I have to find out the magnitude of this acceleration component and this acceleration component, because then only I will be able to get the angular acceleration. Why it is so? Because this unknown, magnitude of this unknown will be equal to what? So let us attempt to write this magnitude. It should be equal to alpha AB, which I do not know yet what is going to be its magnitude, though I have found out its sense, multiplied by the link length AB, which is happen to be equal to R here. So this is alpha AB multiplied by R. And what will be the magnitude of this tangential acceleration of point B? Obviously, this is going to be root 2R multiplied by alpha BC. So, therefore, if I am able to calculate this magnitude and this magnitude, I should be able to get alpha AB and alpha BC. Correct? So now I have to find out the magnitudes of this vector and this vector. So how we can do it? Again, we will be applying the semi-analytical method. This is 50% graphical. The graphical part is over. Now I have to apply the analytical procedure. So how I will be doing? See, I will do it one by one. First of all, since this horizontal line is one unknown is lying on this horizontal line, what I will do, I will take the projections of all these vectors. Remember, this is the resultant vector, this is the resultant vector, this plus this is the resultant, and that resultant is equal to sum of these component vectors. Correct? So I will apply the vector algebra concept. What is that? The component of resultant in any direction should be equal to the algebraic sum of the components of the component vectors in that direction. I repeat once again. What principle of vector algebra I am going to apply? The principle of vector algebra is that if there is any n number of vectors are there, then we know the resultant of those n number of vectors, it has that resultant is another vector and it must be having components in any particular direction. So let us choose any arbitrary direction, okay, and take the component of that resultant of n number of vectors in that direction. Follow my words minutely. Take the component of the resultant of the n number of vectors in that direction. So that component will be equal to the algebraic sum. Means what? Algebraic sum means sum of the, sum means SOME. Sum of the mane kichu component of vectors will be having positive signs. Some of them will be having negative signs. So that's why it is called algebraic sum. Algebraic sum means sum with sign. Algebraic sum means sum with sign, taking care of sign. So what was the principle I was referring to? I said that for n number of vectors I have found the resultant and I am taking any direction and I am telling that the component of that resultant vector in that specific direction is equal to the algebraic sum of all the n number of vectors in that direction. This is the principle of resultant vector that I am going to apply here to solve my 50% analytical part. So since you see this is an unknown, I choose this MM line, which is the vertical line here, as a direction, and I try to find out the component of these vectors in this direction. That means what I will do, I will find the component of this vector and this vector in MM direction that should be equal to the component of the remaining vectors in this direction. Now why I choose this line? Because this is unknown. So if I choose this line, you see this unknown will not have any component. So though I am having two unknowns, I need to solve simultaneous equations. I avoid simultaneous equation. What I do, I judiciously choose the direction in such a way, automatically one unknown gets eliminated. See, this vector is 90 degree with this, so it means this unknown vector is no way coming to disturb my honeymoon period. So what I am going to do, I will take the component of this vector and this vector along this vertical direction. So how that will be done? See, this angle is 40, from the geometry it is noted this angle will be 45 degree. It is from the geometry it is noted. So this is 45 degree, this is 45 degree. So both of them will have positive components along this direction. Because if you break this vector, you see it will have a plus component here. This also, if you take the vector and take the only the y component, it is also having the plus. So what I see, therefore, I write that, you know, this will be AC plus CB, you see, AB dash should be equal to, that means AB dash, where is A? This is A and this is B dash. So AB dash must be equal to AC plus CB sine 45 degree. Now see, this vector is not having any component to this, as well as this vector is not having any component to this. So two vectors out of my life automatically get eliminated. So I have only this vector living with me. So I say that AB dash is equal to AC plus CB sine 45 degree. So if you now put all the values, now it is simple to understand that your alpha BC turns out to be 0. So that is a by mere chance it is noted that alpha BC is equal to 0. It does not mean that since your omega is constant, that's why it is 0. It is not like that. So alpha BC turns out to be 0 here. Though if someone foolishly or unknowingly, you know, puts the alternative correct here, he will be correct, and that is the difficulty of MCQ type question. It does not evaluate the student's real knowledge, because 50% chance is that, you know, accidentally he is able to strike the correct answer. But if he is asked to show why he is telling alpha BC equal to 0, he will not be able to prove that. So that's the thing. So you see here, alpha BC happens to be 0 here. Okay. Now, I am to find out this other unknown. See, I look for its perpendicular direction. So I take this line, NN line, as the perpendicular to this, and I take the projection of all other vectors. You see, projection of all other vectors along this line in N. Along this line in N. Okay. So what I do, therefore, I find here from here that I can write, say, if you take the projection of all the vectors along this, you will find, suppose if I call this way plus, this way plus, this way plus, you see this green arrow, this direction plus, I see this vector will be having a negative component, this vector will be having a positive component, this vector will be having a positive component, and this vector will not have any component whatsoever. So I just write minus AA cos minus AA, it is AA here, this is AA, minus AA cos 45 degree, doesn't matter whether it is cos or sine, but you need to take the proper cos sign, because if it is some other angle, then it will be erroneous. So you should take cos, appropriate trigonometric ratios. So it will be therefore minus AA cos 45 degree plus AB dash cos 45 degree plus BB dash cos 45 degree, and that must be equal to the line AC. So this is the line AC. So if you come and substitute all the values, you find that 1 by root 2, now you put now you see it is not equal to 0. So if that would have been the logic, that, you know, since omega is constant, therefore it should be 0, then both the answers should turn out to be 0. But it is not like that. So again, students, you should take this note that do not judge your final answer looking at partial instantaneous values, because that will give you always an erroneous answer. So you see, therefore, you find out everything, substitute everything, and you find from here that your alpha AB into R, that will be equal to alpha AB equal to 2 omega square. So therefore, what is the takeaway point? Takeaway point for this method is that, first of all, you have to draw the acceleration polygon. That is the first thing you need to do. First, you need to draw the acceleration polygon. After drawing the acceleration polygon, mark what are the two vectors which are unknown to you. Mark them. So, identify your unknown vectors. Correct? Now, take the directions, two directions, which are, perpendicular to those two unknown vectors. Say in this case, this was unknown vector. So, I take this direction, which is perpendicular to it. And this vector was another unknown. So, I take another direction, which is perpendicular to it. So, identify these two perpendicular directions. Now, take the components of all the vectors in these two directions separately. This will automatically give you two independent equations by which you can be able to directly solve your unknowns, solve for your unknowns. So that is the thing you need to follow. This is the algorithm you need to follow throughout your all problems in this chapter. I need to say, when we are specifically dealing with the reference frame, which is translating only, correct? Non-rotating reference frame. For them, this will be the algorithm. The other day, you are asking me, sir, what are the problems we are going to solve? I told you that, say, this is something new. So you solve at least 4 problems from each category, introductory as well as representative, so that it will give you an enough amount of confidence. Now, if you simplify, your methodology, just think of in terms of the algorithm, the way a computer engineer or a coding engineer writes his or her code. It's a well-defined process of algorithm. So similarly, you need to translate the whole thing into the algorithmic process. And if the better you adopt this algorithmic approach to solve your problems, you will see the quicker will be your results. So that's why I told you that you solve at least 4 problems from each category and build your confidence that this should be my algorithm. This is the way I will proceed for solving all the problems here. So that is the whole thing here. So you need to find out the thing. However, all these things are not written in any book. These are all, the teaching experience by, teaching this subject to the students for number of years. We have ourselves devised. This is the best method, by which we can quickly find out everything. So you need to adopt this method at the earliest by solving a couple of more problems, so that the whole thing goes like an intravenous injection into your blood. So this is the the problem that we have here. Now I hope you have understood this, or you have any query, feel free to ask me. Do you have any query regarding the solution which I have explained for this problem? Hello? Hello?
No, sir.
Yes, sir. Is it okay? You understood the thing?
Yes, sir.
Yes, sir. Okay. So,
Yes, sir.
okay. Thank you. So, if you have understood the thing, then we move on to our next problem. So, this is the. হ্যাঁ বলো কিছু বলবে ওই দেখো তোমাকে যে বললাম যে কিছু নেই তখন তো কিছু বললে না হ্যাঁ বলো
এখানে
কোথায় হয়েছে
এখানে ওই যে এ অ্যাক্সিলারেশন অফ বি পয়েন্ট রেসপেক্টিভ টু এ ওই ইনিশিয়ালটা ওটা একটুখানি বলুন ওটা কেন ওখানে প্যারালাল টু ওএ নেওয়া হচ্ছে
এই অ্যাক্সিলারেশনটা কেন প্যারালাল টু ওএ? তার কারণ এই যে দেখছো না এই লিংকটা এবি দিস লিংক ইজ ভার্টিক্যাল। সো ইফ দিস লিংক ইজ ভার্টিক্যাল ইনস্ট্যান্টেনিয়াসলি, তো এর ট্যানজেনশিয়াল অ্যাক্সিলারেশন কি হবে? বি এর রিলেটিভ ট্যানজেনশিয়াল অ্যাক্সিলারেশন উইথ রেসপেক্ট টু এ কি হবে? It will be perpendicular to the radius. What is the radius? The radius is AB. Instantaneously, this radius is perpendicular, so the tangential acceleration must be parallel, horizontal.
Okay, sir.
Okay. So since this link OA is horizontal, so you see this beings this becoming horizontal ultimately. You understand?
Okay, sir.
Okay. Thank you. So, or if any other person is having any doubt, feel free to unmute yourself and ask me the question. Anyway, if you do not, then we move on to the next example. This is another example. It's again another link which is something like this. Again, it is a 4-bar linkage. However, this 4-bar linkage is called degenerated linkage because the other link is not visible. The 3 links are visible, this link and this one itself is a link, but the 4th link is not visible. The 4th link in fact is at infinity, because if you draw a line which is something like this, then this line will go and since it is horizontal, so it will be at the infinity, the other point will be there. So all this this is called infinite link. All these things you will learn in your kinematics of what is called kinematics of machines and mechanisms in your next sem, I believe. So I am not going into detailed discussion to that. Okay. So again, it is a 4-bar linkage, degenerated 4-bar linkage. This is the driving crank, and this is the slider, or you can say it is a piston. It can be also called as a crank connecting rod mechanism in case of cars. So here, what is being given, for a short interval of motion, the link OA has a constant angular velocity. This is the constant angular velocity it is having. Okay, and the magnitude of that constant angular velocity is 4 radian per second. Now my question to it would be, in fact, if I go back to our previous problem, I give you an homework and home assignment that here, if see that here it is being given to be constant counterclockwise angular velocity. What would happen if this angular velocity is not constant? That means if you are given, suppose to this problem I give that, okay, this is omega, and I say this is your alpha. This OA is having an alpha in this direction. Okay. If this is also being given, this is a known parameter as it is known. So if this is known, what will be your acceleration polygon look like? Please draw it at your home and also deduce the algorithm to find out your 2 unknowns like you have done it here. Suppose this alpha is given, this omega is given, and alpha is given in this direction for the link OA. So it is alpha for OA. If this is being given to you, what will be your acceleration polygon look like, and what will be the corresponding angular accelerations of these 2 links? Solve this at your home. Now, coming back to this problem, example, this next example here, it is being given that this link OA is having an angular velocity of 4 radian per second. So you know that by going that, just I like to see that if you try to select any problem from the text, from the book, from this chapter to solve, try to select a problem where both the initial angular velocity and angular acceleration of any link are being given, because that will be the most general case. So if you can solve the most general case, any specific case, it is always you can solve. So here, for example, we quickly solve this problem. This link OA is having the angular velocity of 4 radian per second in the in the clockwise direction. Determine the angular acceleration of this link AB, that means this link alpha AB. We need to find out the angular acceleration of this link, and also angular acceleration of the link for the instant when OA is parallel to the horizontal axis through B. In fact, it looks for only one unknown. Actually, again, there are two unknowns. One will be this angular acceleration of this link, and another will be guess acceleration of this slider B. So AB and alpha AB will be here two unknowns which you need to find out. Here, although our Miriam sir has asked from us only to give the angular acceleration of the link AB, but DN sir is asking from you what should be the acceleration of this piston B as well. Now, DN sir is always a very bad person. So you see here now. He's a very bad person. So
No.
crooked fellow. I always go above Miriam. So what Miriam has not asked for, I always ask for those questions. Anyway, that's a joke. So you see that I take this geometry once again, and again, as I told you, that for doing the acceleration analysis, you need to find out the velocity analysis first, do the velocity analysis first. And now I think velocity analysis should be your cup of tea, because we have solved so many velocity analysis thus far. So you see this, take the pole A. Since your point A will be having velocity in this direction, so it must be having the tangential velocity in this direction. So you draw the line AA first, and then the relative velocity of B with respect to A is always going to be perpendicular to this link AB, So draw a line parallel to this. I mean to say, here I have drawn this line, I have shown you for you. This is a reference line. This is going to be perpendicular. This line is actually perpendicular. This is perpendicular to this link, correct? So I draw through this a line parallel to it. So this is the line that I draw. And since the point B is only allowed to move along the horizontal direction, either this or that, so the absolute velocity will be horizontal. So through pole A, I draw a horizontal line, allow these two lines to come and intersect at point B, and we get this right angled triangle. Now I solve this. This is one unknown, this is another unknown. So I solve for the unknown AB. So AB unknown is found, this small AB is found like that. It is going to be 0.3 meter per second. Just apply your angles and all, simple geometry. I believe that I need not explain what geometry is applied here. Only thing to note that the relative velocity magnitude must be equal to what? It should be equal to, the angular velocity of this one into the link length. So 0.3 meter per second must be equal to, the omega AB into 0.2, as I was telling. So omega AB must be equal to, therefore, 1.5 radian per second. What will be the direction? Mentally, you put this vector here. This is the arrow that you have decided. So therefore, you see this link should rotate in this direction. So the angular velocity must be in this sense. You must mention the sense. The sense are all, because you need to find out, determine the angular acceleration. See the question. Acceleration is never a vector, is never a scalar quantity. So if someone stops only giving the magnitude, he or she will get 50% answers, 50% marks, because the remaining 50% he or she has not reported. So you have to be very careful. So you see, omega AB is this one. Okay. Now once this is done, now I come to draw the acceleration diagram. See the acceleration diagram. First note the acceleration of point A. First see the acceleration of point A must be towards the point O, and the magnitude of which is of course known to us, that is omega square into the link length. Link length is 0.06, so we can very easily find out how much should be my the acceleration of point A. So this acceleration diagram, this vector, blue vector, considering point A as my pole, this blue vector is drawn. Say I get the point A. Okay. Now after getting the point A, I note that point B will be having a normal component of acceleration. Sorry, I show the arrow properly. This point B will have the point B will have a normal component towards A like this. So this will be the normal component of acceleration. So what I do, I through the point A, I draw this line parallel to this BA, and I get the point B dash. Through B dash, I draw this perpendicular line. Correct. So this is actually giving you the acceleration of point B relative to A tangential, and this is unknown. This is unknown. So, and the magnitude of which should be equal to, at the same time you write the magnitude, alpha AB multiplied by 0.2. Okay, so that should be the magnitude. So this is not known to me, so I either way proceed this line. Now you know the point A, come to the point A, see the point B's absolute acceleration must again be along the horizontal line. So I draw another line through pole A which is horizontal. So you see this line I draw, it can be drawn in this direction, but my objective is to intersect this line with the other unknown. So I draw. So this is another unknown. So this is actually the acceleration of point B, which is unknown. So this is unknown. Okay. Now you have, this is another right angled triangle you get. Now it is very simple to solve the unknowns. Again, you see this is one unknown, this is another unknown. So I have to find out therefore, the alpha AB only. So alpha AB only, since I have to find out, that means I have to eliminate this AB. No one is asking from me what is AB. Since it is unwanted unknown here, right? Actually in this equation, in this question, nobody has asked for the acceleration of point B. So that's why since this becomes an unwanted unknown for me. Since it is an unwanted unknown, I need to find out its perpendicular direction. This perpendicular direction is of course vertical. So draw a vertical line, a reference vertical line for that matter. I draw a thick line for you, which is the reference line. So take the projections of all these vectors. I mean to say this vector, this vector, this vector, and this vector. Of course, this is unknown, so it is not coming and affecting your life. So therefore, take all the components of these vectors along this line. See, this is also horizontal, so it is also not coming. Though its magnitude is known to me, it is not interfering. It's a good friend. So he is not disturbing myself. So this unknown is eliminated. I have already eliminated this unknown. So this is gone from my life. This is so good friend to me. He is not bothering me. So naturally I have one vector here, another vector here. Actually, this is the resultant and these will be the sum. So you see the resultant is 0 because resultant is not having anything. So the resultant component along this line must be 0. So it means the components component along this line must also be, the total sum must be 0. And that is also corroborated because this vector is having an upward component and this vector is having a downward component. So naturally these two will cancel and will be equal to 0. So it is pretty simple. Just apply also you can apply the property of triangle as well. to find that AB dash sine theta must be equal to B dash B cos theta, or you can take the components. I have shown here the component philosophy because this is the algorithm on which we have relied to solve all our problems. So I have therefore gone for component philosophy here, though for me, fortunately, the acceleration polygon becomes very simple. It becomes a simple right-angled triangle. But it may not be all the time. I may not be lucky all the time in that way. So therefore, I rely on the component philosophy and find out the remaining things. And the remaining things already I have explained. So put all these values and you will get the relative tangential acceleration. So the angular acceleration of the link AB, since its sense is in this direction, so put the sense here. So you know that in order to have this sense, you see this angular acceleration has to be in this direction. So it is to be in the counterclockwise sense. So that way I therefore is able to answer all the queries with me. So dear students, today we stop here because it's almost the time that we are hitting 4:30 hour limit, and we therefore finish our the discussion on the relative acceleration method and the velocity method. Both we have finished for the non-rotating reference frame. So when we will be meeting next time, you see that we will be discussing the Baba, এখন কে রে? VB Ghu. Who is that fellow? VB Ghu. Hey, VB Ghu. Who is VB Ghu?
জানো না স্যার।
হ্যাঁ
স্যার জয়েন করাতে হবে না স্যার এখন আর
স্যার অন্য
অন্য সব স্প্যাম ফ্যাম করে ওসব
ও আচ্ছা, তো না সে তো জয়েন তো করাবো না বটেই, সে তো ওই জন্য আটকে রেখেছি গেট। ভিভি ঘুটা কে আমি সেটাই জানতে চাইছি। কে গো এ আমাদের বিশাল? হু ইজ ভিভি ঘু? ডু ইউ নো হিম?
সিনিয়র স্যার, এই প্রোগ্রামের ছাত্র নেই আমাদের,
এরকম কেউ নেই।
স্ক্যাম স্যার, স্ক্যাম।
ও আচ্ছা, হতে পারে। আচ্ছা, তো এনিওয়ে আমরা we stop here. So next time when we will be meeting after the Diwali break and all, we will be doing the relative acceleration with respect to rotating reference frame. And at this point I stop my recording here just to tell you one thing. When will be your